Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve this stress analysis using Salome meca. Salome meca having a pre and post processor which is open source, and it has a solver called aster, and it is wonderful for finite element, wonderful solver for finite element analysis. Now we'll go for Salome meca. We'll use geometry model or shaper model. So here see using angle we just want to define this point. For that, so this is we'll use shaper model. Just go to shaper, this is shaper model, go to sketch. So I will use XY plane, just rotate it. This one is the XY plane, see. So this is Y and this is X, this plane is XY plane. So set the plane view. So now I have set the plane view. Just go to the model. First we will create one line of total length 6 meter. So first take the line. So I'm starting from 0, one line. So then one more line and connect with this. Now I have connected. Now see, this is horizontal line. The angle between these two lines is 60 degree. This is 60 degree and this also 60 degree. So first what we will do, so we'll make angle. So just click this one, and angle between this is 60, and similarly angle between this is 60. Now we have made the triangle. Now finally we just want to define this length. So there is an option called this one. So this length is 6. Now it is coming very small. Just click it here. Now I just closing this. Now this, just take this angle here and take this angle to here and take this dimension to here. Now go for fit screen again. Now we have got this. Now this again we can make it here. This length we can keep it here. This is 6. So now we have created this equilateral triangle. Then we just want to make one line here, and here and here we just want to make a line. Now just go here, take the line, so click it here. So there is a horizontal line, then connect it here. Then again just click it, just go to sketch, again go to edit, then again go to line, click it here. Now detach, escape, go to line, make it here, and connect it here. This is vertical line and this is horizontal line. Then finally we just want to make one center line here. Just go to line, click here and connect it here. So this is our model actually. Now we have created our model. It shows green color, that means that it is fully constrained. Now click this one. Now we got this one. Now we can export this sketch in step file or brush format. Go to file, export to CAD format. Now we just want to save it. Just go to computer, pictures, aster, Truss. This is the 4th case. I'm just naming as Truss _1. Just save it. Now we have to choose the file. I have selected this file. Now see, it is generating the surfaces. Now tick this green color. If you are not selecting this surface, it will not show the tick green color. We have to select the surface, go to tick. Now it has exported there. Just go to the location. See, the Truss _1 brush file is exported here. Now we'll use this file to create the groups. Now I'm going for geometry module, go to file, import brush, pictures, code aster, truss, fourth case, open it. Now I opened here. Now it will come like a face. Now we need to extract edges from this face. Go to new entity, explode. There is an option called wire, apply and close. Now we have got 4 wires, first wire, second wire, third, fourth. Then we need to make all the wire into single wire. Just select this all wire by press shift and hold, go to build wire, apply and close. Now click so only. Now we got this model. So now we can go for grouping. Right click, create a group. First one is select all, make truss. Just apply it. The first group is a element edge group I have created. Then we need to apply fixed boundary condition here or roller boundary condition here. For that we need to create groups. So go to point low, select this point, add, fix, just apply, select this point, add, make it roller, just apply. Now we need to apply force in remaining nodes, 1, 2, 3, 4. Remaining 4 nodes we need to apply force. I'm just naming from here, force y in 1, force y1, force y2, force y3, force y4. Like that I'm naming it for easy understanding. So point, add, this one is force y1, just apply. This node is force y2, just apply. This node is force y3, just apply. And this node is force y4, apply and close. Now see, so I have created all the groups. We'll check one by one. This one is a complete element edge group, that is truss, to apply the cross section and apply the model, everything, apply model material property. For that we need to create this truss. Then this one is the fix, we'll enable this one. This one is the fix, and this one is the roller. This one is the force y1, this one is force y2, this one is force y3, this one is force y4. Now we'll check the case. So here we just want to fix it. Here there is a roller support. So remaining areas we need to apply the force. Now our groups are correct. Now we will proceed to the meshing. Before that we will save this file. Go to save as truss. I'm just saving here study2, just saved it. Now we'll go for meshing. Go to mesh, select this wire to mesh, create mesh. Now it will show only 1D and 0D. Just choose wire discretization. Here choose local length. This is, you make it 0.2. Say OK and apply and close. Right click, compute. Now see, it has generated 195 nodes and total number of element is 198. Just close it. If you want to see what type of element it is, go to modification, add. So this is add node. From that we can see it. These are nodes. So this one is edges. Similarly we can go for add edge. Like we can so this is actually linear element. Go here, go to mesh information. See, this is a linear element 198. Now just say OK. Now check the groups. So all the groups are came here. These all the groups are nodal groups, and this one only one is edge group. Now we can save this file. We can proceed to aster study. So use stable version always. Say OK. Now we just want to add stages. Add stage. Go to mesh, read mesh. So we'll read the mesh one by one. So this is my mesh med. Say OK. Now we need to define the model. Go to assign finite element. So we can apply to everywhere. Go for mechanic. Here this is actually a beam element we are going to use. So for that, so this one POUDT, this is Timosuke beam element. Say OK. This is mesh. Say apply. Say OK. Now we have defined the model. Now we need to define the element property. This is beam element because we need to define element property. This is beam. Go over poetry. Edit. Section is a rectangular section. For all the cases I am using common section. So this one is 0.1. So sorry, this one is HY, HZ. Breadth and width both are 0.1. So group element, we need to define the group of element. Truss is the element we need to define. So edge element I have chosen. Say OK. Say OK. Just scroll down here, model, just apply it. Say OK. Now model definition we have done. Go for material. In material we need to define material first, then we need to assign the material. Go to define material. So keep this name. This is the linear isotropic material. Young's modulus is 210 e power 9 and Poisson ratio is 0.3. Say OK. Just apply it. Say OK. Now I have defined the material. Now we need to assign the material. Go to mesh. Mesh is this one. Model. Go to this one. Edit. Everywhere. Material. OK. Apply it. Say OK. Now we have assigned the material to the mesh. Functions and list are not required. We just go for boundary condition and loads. Here we need to assign mechanical load. So we need to fix it here. One by one we'll do. First, enforce degree of freedom. I'm going to enforce all the degree of freedom and this node. So first choose the node group. Here you can see at least one. Choose the node group, edit, fix. So you can hide this coordinate. This fix node is selected. Say OK. Now we can put 0, 0, 0, 0. Now we have done applying fixing boundary condition. Now what we want to, we need to apply roller boundary condition here. Say OK. So just add one more. Edit, node group, edit here. So roller, you just tick it, you see it. So this is the roller. Say OK. Here we need to fix it. So just switch on this coordinate. We need to leave the x-axis because x-axis it has to free to move. So I'm just leaving this x translation, remaining I'm arresting it. So these are not required anyway. I am fixing here. So I've done. So just say OK, just apply it. Now we have applied fixed boundary condition here, roller support here. Then we need to apply forces. We can apply boundary condition load in a single command. Just scroll down here, separate it also we can do, but it's easy to apply in single command. So here you see it start from here, force nodal. Click it here. We need to apply 1, 2, 3, 4 forces. 1, 2, 3, 4. One by one we'll define. First is choose the group node, force y1 here. Say OK. In y direction it is 10 kN. We need to apply in Newton in software. So 10 into 10 power 3. So in y direction negative 10, just add 3 zeros. 1, 2, 3. 10 Newton. Yes, 10 kilonewton. So say OK. Now go to second edit, group node, edit, force y2. OK. Now just go here. This is 15 kilonewton. So for that, y minus 1, 5, 1, 2, 3. Say OK. Go to edit again, node group, force y3. Say OK. Now check the third value is 20 kilonewton. 10, 15, 20. Fy minus 20, 1, 2, 3. Say OK. Go to edit, group node, fourth force. Say OK. Fy, just go to the PPT. Here it is 10 kilonewton. So Fy minus 10, 1, 2, 3, 3 zeros I have added. Say OK. Now I have added all the forces. So here by moving cursor here, you can see what we have applied. This is a force y3, force y2, force y1. So everything we have specified. Now scroll down here, there is a model. Just apply it. This is our boundary condition and load. Say OK. So now we have applied all the boundary condition and loads. So pre-analysis is not required for this. Go to analysis, static analysis, material, element property, model, you choose it. Now go to loads, edit. So only one node, just say OK, just apply it, say OK. Now I have solver, I have defined the solver. This meca static solver will calculate the primary variable displacement. If you want to see 1v stresses, principal stresses, directional stresses, we need to derive the values from this solver. So go to post processing, calc champ, use the same name, lin. Now go to constraint. Here we can choose directional stresses. Similarly, criteria we can choose here equivalent stresses. So LNO is nothing but elemental and this is nodal. So result is in model, material and structural element. Everything I have defined. From that it has to calculate. Apply, say OK. Now I have calculated stress everything. Finally we need to save the results from this value. Go to output, set output results. Here click the three dots, go here, pictures, code aster. There is an option called stress. My case is fourth case. I'm just saving this .rmed. this is required. We need to save it as RMAD to open in paraview. So I just result dot RMED save, just click it here, edit, mesh, result. You have to choose CalChamp, element property, remaining here you see TouchChamp, you just make it S, save OK, make this format as MED, just apply it, save OK. Now everything I have specified here. Now we can save this file and we'll run it. I'm just saving here. Go to history view, click this plus button and click this keep results. It will keep the results. Make this into 5 seconds, run it. Now it is solved. Yes, it is solved with the alarm, it seems, because it will not calculate directional stresses. There are different calculations are there. That's why it's showing some alarm. SIEQ, everything it will not derive for beam element. For that we need to define. Go to CalChamp. Here we need to define EFGE no. Here we need to do SIPO no and SIPO node. From that only we can extract the normal stresses and bending stresses. Here nothing will not come, so just close and untick it. Here there is force nodal force we can, and reaction force we can calculate. So reaction nodal, that is I wanted, so I'm just switching on it. So I'm just saving the file, apply, save it. Now I edited this CalChamp. Just go here, delete the old results. Now just save this file, go to history view, click these two buttons. Now run again. Now it has solved. Just go. See, there is no alarm because it has calculated whatever we have given, which is correct. This only we can extract from the beam element. Now go to paraview to view the post results. Now it is suddenly closed. So sometime it happens. Just open Salome again. Just go here, paraview, open, Vengat. So pictures, code aster, trusses, the fourth case. This is the output file, result.rmd. Say OK. Just apply it. Now we can go for displacement. So we used to see the results in blue and red, so I'm just going for blue and red, rainbow, blue to red, apply, close. Here we can make it this into 12. So this is the way other commercial softwares are showing results. Now if you want to see displacement in y direction, this is the displacement in y direction. Displacement in x, displacement in z. Displacement in z is almost 0. Now we can go for reaction nodal. We are fixing these two locations. Here we are fixing, here we are having roller support. So we will be having nodal forces here. So x, y, z nodal forces, reaction forces. So now we can go for SIPO. The first one is normal stress in the member. These one are normal stress along the x-axis. This one is bending stress in y-axis, bending about y-axis, bending about z-axis. These two are shear stresses. These two are shear stresses. This is stress due to torque. So now we'll see the normal stress, bending stress. This is almost zero. This is torsional stress almost zero. Shear stress is also almost zero. So shear stress about Z, it has a value of 4.7. Similarly, you can go for normal stress. This is 9.9 e power 5. This is the maximum stress generated in this number. Just go here, change the color into blue to red, just apply and close. This is make it tool. So in that we have seen, if you want to see the reaction force in any one of the point, so just go here, go to views, windows, make sure you have selected the selection display inspector. So here you can see selection display inspector. Go to points, reaction nodes. Now we'll select this node. I just want to select only one node. See here, reaction force at x is 0. Reaction force at y is a value of maximum, because there is no x forces. So the x reaction force is 0, but this is a y reaction force. Similarly, we'll be having y reaction force there also. So just closing here. If you want to see stress, so what is stress in this point? Just close it. Zippo. Just split screen. Pads coming maximum. Here the compressive stress is the maximum. Here this node, this element having more stress, compressive stress, and here it has tensile stresses. Now we'll select one node here. So here the normal stress is 987950. Similarly, we can select here the compressive stress, see, -2. So in that way we can check the stresses and reaction forces in stress element. Thank you for watching my video. Please subscribe my channel for more videos. Thank you.